And if you do not have the right evals, you cannot track your progress at all, and you are not going to improve as a scientist either. We have two main libraries, LLM Evaluation Harness from Eluver AI, and we have Light Eval from Hugging Face, but they don't have everything. So you're actually relying on like a ton of other benchmarks on in individual libraries. There's a lot of issues with compatibility and all that stuff. So actually evals is really a big problem, but it's important to maybe start with a narrow focus and then expand later.
Let's talk about the LLM scientist roadmap. Step one of the roadmap is understanding the LLM architecture, which you had 4 parts. And the first part is understanding the GPT decoder style models. So can you explain how this kind of works on a high level?
Yeah, so the distinction here is about
how would you approach the market as an early career professional, especially in the US, in addition, also in a small region. So I come from a small country in Trinidad, very different kind of vibe. Opportunities are not there. So I think your contributions in open source really open doors for folks who don't have access. But what's your thought there?
Showing your work in general is something that really works. And even if you do not want to do open source contributions, I think that joining a company that allows you to show your work openly, publicly, is something that is very valuable in the long term for you.
Today, we're going to get the roadmap for becoming an LLM scientist and an LLM engineer with Maxime Labonne, co-author of the LLM Engineers Handbook, creator of the LLM course on GitHub with over 40,000 stars, and the author of Hands-on Graph Neural Networks. Maxime, welcome to the AI Portfolio Podcast.
Thank you. Happy to be here, Mark.
So give us an overview of the 2 books that you've created and the course that you put out for free online.
Yeah, it's going to be a long overview maybe, but
sure.
I wrote the first book about graph neural networks. It was in 2022, and in my position at Airbus, this is something that I encountered because I work with computer networks. And the first thing that I was interested in was transformers, but the transformer architecture was not really meant to be used in this way. At least it was not the best architecture to do that. So I was interested in graph neural networks because they offer a good representation of what a computer network is, because they can represent graphs and they can learn embeddings with the nodes of this graph. So it was kind of a natural extension. So I did this book, and then I think I burned out with GNNs. I was not interested anymore. I think, the book is like a lot of deadlines. You have to be constantly churning content, and at the end of it, I was done with GNNs. I didn't want to work with it anymore. So I went back to explore the transformer architectures a bit more, and this is when it got a lot of traction. I changed position because I wanted to work with large language models, and I got a position at JP Morgan specifically for that. And this is when ChatGPT was released, like a few months after that. And then everybody wanted to do LLMs magically. So I had a lot of questions because I was one of the people who worked with the transformer architecture for years at this point. And all these questions made me think that maybe a course would be quite nice actually to be able to refer to something that is kind of like, okay, because basically the main question was, how do I learn about this stuff? How do I become an expert with LLMs? And I created the first version of this roadmap that was really tailored to learn a lot about LLMs. And then the job of people working with LLM kind of changed from scientists to engineers, because suddenly we had a lot of people from different backgrounds, from software engineering, from cloud engineering, a lot of different subfields were interested in how to use these LLMs in their work to build apps for certain use cases. And I decided to split the course into 2 roadmaps, one for scientists. This is the one I'm most comfortable with because this is more like my background, and another one for engineers. And this is really, I would say, inspired by all the questions I've had and how I see the job evolving in this regard. And based on that, I was also contacted by my publisher They were quite happy with the success of hands-on graph neural networks, and they were like, "Hey, we think that a book about large language models would sell pretty well." And I said, "No, I'm not in the mood for that. It was too much. Writing a book was too much. But maybe if you find me some co-authors, I would be able to kind of recycle some content that I've written with the blog post and content for the LLM course, and I would be able to make something that is not too difficult for me to produce. We had to find like a few co-authors, but in the end, like I found the right person who was also like super interested in this and who had the LLM engineering background that I lacked. So he brought a lot of hands-on experience about best practices, MLOps, how to build reliable pipeline, how to deploy it properly on AWS. And this is what this book is about. It's really about how to become an LLM engineer. And through that, we see like the main techniques and we try to exploit through the lens of MLOps and the best practices to increase the maturity of the field and be sure that the application that you deploy actually works, is reliable, is robust. So this is kind of the idea behind this book.
Fantastic. So it seems like you got hustled into doing a second book.
Yeah,
So
absolutely. They forced me to do it.
I do like that fact that you're as a maybe an aspiring author. And I think a lot of folks think about writing books, and it's nice to hear that it's a fairly painful journey, and it's not all that it might be cracked up to be. And it's quite interesting that you got burnt out of GNNs and you had that same resistance for LLMs, because I'm sure you didn't want to break break that relationship internally.
It's true. It's true. I think that it's a lot of work, and you always go with the idea of making a book with some kind of hack, like, oh yeah, I have some articles, I can recycle them, and it's going to make a book. But it never works out for me. I don't understand. Like, actually, I just produce original content for the book. I really recycled very little of it because
Hmm.
some part was just not up to date anymore. So you need to rewrite them to be up to date. And yeah, in the end, it kind of backfired. But I'm glad it's released now.
Yes. What would you say is the main distinction between an LLM scientist and an LLM engineer? And maybe is it better to say AI scientist, AI engineer? What do people in your world call it?
Yeah, I think there are a lot of different job titles, and even the job titles are not super specific because you can see AI scientists doing a lot of engineering, and the opposite is often true too. So yeah, I would say that maybe fine tuning is something that is a bit common between both worlds
Mm-hmm.
from my
Mm-hmm.
perspective. I would say that RAG would be more of an engineering problem because you need to deal with databases, you need to deal with more robust code, higher quality code, not something that scientists are really good at in general. So fine tuning would be kind of the middle ground. I would say maybe a bit more scientist than engineering because you need to have a background, I think, in data science to be able to really understand what it means when we want high quality data. This is really the crux of the issue. Like the quality of the data is what matters a lot. But yeah, that would be the middle ground in my mind.
It's a good distinction for the quality of data, and it's probably interesting where the intersection of an LLM engineer and a scientist sort of intersect in terms of the volume of data that has to come in, the transformations that have to occur at scale, especially at scale when you train very large models. So quite interesting. So you've gone through some journey, right? You work as head of post training at Liquid, and you've seen a lot of things. You've come from, I guess, the banking domain, the Airbus domain. If you were to do your journey over again and you wanted to end up as a super expert as you are today, what would you kind of do differently?
I don't think that the career is that interesting and it didn't really play out a major role for me. I think what really helped me was my open source contributions. It
Hmm.
was my articles, the books, the course, all of that. And the fact that I could show my work because I released fine-tuned models on Hugging Face and people noticed. And this is, I think, a very healthy way to promote yourself, and even like for companies to already be able to evaluate your work. Because if you are hired in a post-training team, a lot of the time it's quite difficult to find if people like have experience with it, because when you fine tune models, you're going to see common problems, common pitfalls, and all of this stuff is something that you need to go through at some point. And companies not necessarily want to train you for that. So I think this is quite good. And to answer your question, I was able to do that at Airbus and at JP Morgan. And I think this is kind of the key. In other positions, for example, working for a startup, it can be a lot more difficult to have time on the side to do this kind of work. But working for really big companies can also offer you more spare time for your hobbies. And this is what I managed to do. So I wouldn't necessarily do things differently. I would maybe try to get into companies that are more AI focused, like NVIDIA, for example. But I think that anything is fine as long as you're able to show your work and produce interesting things.
Do you think it's necessary to have a degree to become a good LLM engineer or LLM scientist?
Yeah, not at all.
And do you have a PhD? It's
Yeah.
interesting that you're saying that. We both have PhDs, actually.
No, I think that you agree with me, but we see a lot of people who are just passionate about it, and the passion makes them like kind of work a lot or read a lot of content, that kind of things. And of course, like if you spend a lot more time on the topic, well, you're going to be a lot better than people with a degree, because the degree doesn't really apply here. Nobody had, now it's kind of true, but nobody really has a degree in modern LLMs, because this is just science, this is just research. So it's not like there's a lot of competitive advantage of having a degree in this field. I think it give you a solid background to understand how this model work. And if you explore LLMs and you want to go really into the science of it without a degree, you might hit some walls because you're limited by, I don't know, math, by lack of background in statistics. But all of these pitfalls can be overcome by more work, by actually getting better in statistics, for example. I learn how to read papers efficiently, but there's no, I think, real advantage of having a PhD in this field if you want to build applications with LLMs.
All right, I think you put the stamp in it. No, easy on the PhDs, I guess. If people are thinking about that, the natural question. We're going to get to some very technical questions coming up soon. But the natural question I think everyone has is, especially as they observe LLM scientists versus LLM engineers or AI engineers, how long would it take me? And I know it's naturally dependent on where I'm coming from, but on average, if I went with probably the same intensity that you've gone over that period of time, given that created a roadmap, what's sort of that expect time to be a functioning LLM scientist?
I don't think it's very long. It depends how much focus you put. Because, for example, you can be super interested in fine tuning, and if you're only interested in fine tuning, then the scope is a lot smaller than if you're interested in pretty much everything. I would say, in general, a few months is probably like
Wow.
kind of the goal. If you do it regularly, um, there's a lot of resources that I reference in the course to help people to find the right references to explore. The course is not really a course, to be fair. It's more like a curated collection of articles and references with a roadmap to help you learn this stuff. But there's little original content. It's mostly my own articles. And yeah, it really depends on your focus. And of course, your background is also really important, because especially if you want to specialize in the engineering aspect of LLMs, having a background in software engineering, MLOps, cloud engineering is something that can be very, very beneficial, because like the inference, the deployment side of these models is really reliant on AWS and all the classic traditional cloud providers. So you would have a lot less to learn if you do that. I would kind of encourage people to first take something that is quite close to what they're familiar with, because everybody has a background. So if you have a background in cloud engineering, it's better to first start with cloud engineering and then explore a bit more the other things that might interest you to see if there's something that you're really passionate about. But it's better to start the journey from an easy entry point where you don't have too much to learn immediately.
Interesting. So we're coming into some space and just coming from the space where you are. Don't try to enter through a door that you're maybe not prepared to enter, essentially. I've been watching this show called Dark Matter on Apple TV. So it's quite interesting. And, he goes into all these parallel universes and every door you open is completely unique. So this kind of reminds me of that. I could open, let's say, the pre-training door. I have absolutely no business being there in some cases.
Don't go to that dimension, no.
Yeah, it's a different dimension. So I think the things I'm very curious about is, can you make contributions as an LLM scientist if you're not on a team? Because oftentimes I think the notion of an LLM scientist is, huge training, huge models, and that typically requires a ton of folks working on the problem. But as an individual LLM scientist, what kind of impact do you think folks can drive?
Yeah, you can have a lot of impact. Like it's really crazy, like how easy it is actually.
Okay.
Just people don't do it, to be fair. But just like merge a few fine-tuned models together, do a DPO run, all the code is there. I've written articles, other people have written even more up-to-date articles about this stuff. And you're probably going to end up like top of the LLM leaderboard with just like one or two tries. It's not very complex. You can just reuse a really good instruct model, for example, Qwen 2.5 7B instruct. Do a bit of DPO, and it's probably going to improve performance. It might not improve performance all across the board. It might be more limited to one thing, but if you have a good preference data set, it can work like very, very well. And merging models is also another technique to like reuse what's out there, recycle models that other people have trained. And these trainings are quite expensive. Sometimes they can be like really large scale trainings. And yeah, for cheap on a CPU, you can just merge all these checkpoints and get a really good model. I think that the hidden aspect of what I'm describing is that you need to be very strict about evaluations. Evaluations are really what are going to guide your optimization process. And if you do not have the right evals, or you cannot track your progress at all, and you are not going to improve as a scientist either, because the experiments that you make, you cannot really measure the outcome. So I would say that first of all, having the right evals is the most important stuff. And it's difficult because in this ecosystem, evals pretty tough. Like the libraries, we have two main libraries. I would say it's LM Evaluation Harness from Eluver AI, and we have Light Eval from Hugging Face. These two libraries are good. They allow you to access a ton of different benchmarks, but they don't have everything. So you're actually relying on like a ton of other benchmarks on in individual libraries. There's a lot of issues with compatibility and all that stuff. So actually evals is really a big problem, but it's important to maybe start with a narrow focus and then expand later, but getting it right immediately, even before you start your fine tunes.
So eval, when you say eval, this is just the size of the data set, quality of data set, running the models against that, splitting training test set. Is there anything? Yeah.
It's a good question. It's a good question. When I talk about evals here, I'm really talking about benchmarks like MMLU, like HelloSwag, like IFEval. So those traditional benchmarks, but you can also have benchmarks that are specialized in code, for example, human eval, MBPP, and those two are quite traditional. They're not very good, but they're quite traditional. And you have a lot of other benchmarks. I'm talking about MBPP, I'm talking about MMLU, HelloSwag, IFEval. So all these benchmarks, you can find them either quite easily in these libraries because they already have implemented them, or you can use other libraries that are more dedicated to those. And this is really the complexity of it. It's about managing all these different libraries with different compatibility issues. And this is what you should try to achieve in the long run. But first of all, it's better to have a more focused approach with a few benchmarks that you can expand later on.
So when you go to fine tune a lot of these models, as for practice, you leverage current things that are out there, and how much of your workflow comes into you developing your own fine tuning data set, and oftentimes what's a decent number of samples that you need to have, and is that actually correlated to the size of model? So I have a bigger model, I need more samples, or bigger models are supposed to be more sample efficient, right?
Yeah, exactly. So actually, if you have a bigger model, you can have fewer samples, which is quite nice because at least you save up in terms of number of samples. There's a lot of different approaches. I would say that the traditional way of doing things would be to take a base model provided by an LLM provider like Meta, for example, and then you would apply supervised fine-tuning to this base model. So you would have an instruction data set. If you're doing a general purpose fine-tuning, this data set would be about 1 million samples. You can see a lot of different examples of this kind of data sets. I also have a GitHub repo listing a lot of these general purpose data sets. And when this is done, you can either say, okay, we're good, or you can apply preference alignment techniques to be able to refine the quality of the answers. Preference alignment techniques were quite optional last year. Like it wasn't a big thing, but now people are really used to this preference alignment layer, I would call, on top of the models. And when it's missing, people think that the model is bad, but it's actually not a problem with the knowledge of the model. It's not a problem with the capabilities of the model. It's because we are all super used now to get really helpful and long verbose answers. You can see it if you use ChatGPT. If you ask GPT-4o any question, it's going to produce an entire essay about it with headers, with Markdown. It's really over the top, but it kind of hacks the human mind into thinking, oh, this response is really comprehensive, so it must be really high quality. But actually, it's not true at all. This is completely different. You can have models outputting extremely long, well-formatted answers, and the answer is completely wrong. Or you can have a model that outputs just one line, and people would be like, no, this is probably not true, but actually the answer is correct. So DPO has become more and more important. And beyond this kind of preference alignment layer that I'm describing with helpfulness, it also improves the capabilities of the model quite a lot. So it's important to have a really high quality preference data set. And it's especially important for preference data. It's the final stage of training. So if you do DPO run, you really need to have the highest quality samples because otherwise you are not going to improve the model. On the contrary, you might degrade it. And currently it's quite difficult to find open source data, preference data that is super high quality like this. So it's a bit of a challenge, but I think this is great because any challenge, if you're a solo contributor, you can basically create data sets and upload them Hugging Face. People will notice, people will use your data set, you'll be credited, and you can even use your own data set to create your own fine tunes.
You're spitting some game. When you do DPO, this is a full excuse me, you're changing all the weights? Or can you explain a bit more about DPO and how it
Yeah.
works?
So DPO, like supervised fine tuning, you have different techniques to train them all.
Sure.
You can do full fine tuning where you're going to retrain 100% of the weight of the model. This is what LLM providers do. For example, when Meta applied DPO to Llama 3.1, this is what they've done because this maximizes the quality. The issue is, especially if you're on your own, so paying with your own bucks, it's very expensive to do. So you might want to use more parameter efficient techniques. There are two of them that are very popular. It's LoRa and QLoRa. The principle behind LoRa is quite simple. It's instead of retraining every parameter of your model, you're going to freeze these parameters, and between your layers, you're going to add adapters. These adapters are really small matrices, and you're going to only train these adapters when you do your supervised fine-tuning. By doing that, you are going to retrain the equivalent of 0.5% of the entire parameters of your model. So it's a lot more efficient, which means it's a lot faster, it's a lot cheaper for you. And a way to do it even more efficiently is QLOA. Q is for quantized. And this time, instead of loading and freezing the model in the original precision of the weight, you're going to use lower precision, 4-bit precision instead of 16-bit precision to be exact. And it means that you need even less VRAM to load the model, so it's even more efficient. But in this case, you're going to see that the quality is a bit degraded by 2-3%. So it can be a good compromise. But when you have enough VRAM, I would recommend using LoRa because it's higher quality and it's also faster to run.
And just for those listening, DPO is direct preference optimization, correct?
Yeah, exactly.
Is that where models get, at which stage in the model training process, we're going to go through your LLM scientist roadmap, but at which point in that process do I get the personality of an LLM?
It's a good question. I think it's at every level, to be honest with you. And they change the personality of the LLM at different levels, and DPO would be the best one. The preference alignment is really good at changing the personality and the writing style of the model. So that would be what I would do because it's also easier to do, to be fair. I don't want to pre-train the model just to have a personality. It would be quite difficult to do on top of that. So
Yes.
DPO would be where you want to do it because it's a lot more sample efficient to do.
Yes. And when it comes to personalizing models, so right now there's one model, we all prompted the same. It to some degree has a single personality. Are you seeing where, just like a LoRa, I'll have an adapter for understanding math, I'll have an adapter for understanding, physics, whatever the case may be. Are you seeing that same thing play out in the DPO realm, where is it the same adapter if I do an adapter-based preference optimization?
Yeah, it's a good question. Yeah, it would be the same adapters and you could use it in the same way, to be fair. But I don't really see it in the wild. Now that you mention it, I'm thinking of examples, but I can't find any. So yeah, you could have a DPO for like one personality, a LoRa for one personality, a LoRa for another one. And maybe this is how some companies use them. I wouldn't be surprised if that's the case.
Yeah, because I was thinking about it from a prompt perspective, and hopefully maybe you can give me some intuition. So when I prompt something, I'm thinking of it. I have an entire distribution, and when I prompt, I'm conditioning that distribution. So I'm making, I'm reducing that. Let's call it a search space of tokens, or the search space of how tokens go one after another. How much of the personality can I create through prompting versus something like DPO?
Yeah, it depends, I think, on the personality. It depends on multiple factors. The first one is the data that the model has seen. Like, can it actually create the personality that you want it to create? For example, if you want to have a fictional character as a personality and you try to prompt it to tell it, like, act like this character, if it's not in the training data, it's not going to be able to do it, of course. I think that through prompting, you can get a lot, but through DPO, what's really nice is that you can do both. And the way that you create your preference data set is kind of like a feedback that you give to the model, because you could start with prompting and you are going to manually evaluate every answer. You're going to say, this answer is good, this answer is bad, this answer is good, this answer is bad. And with preference data, we give the same prompt a chosen answer and a rejected answer. So you could create your data set that way. Ideally, you could have like a version with the prompt, without the prompt, or with different models and the same prompt. And that would be a natural way of creating your DPO data set. So you can go beyond just prompting, and this will allow the model to actually understand what you are looking for when you prompt it that way, how it should really react. And if there's something that annoys you, for example, the model could say, like, as an AI assistant, blah, 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 you could really remove that from the data set or add it as a rejected answer. And in this case, the model will learn not to output that.
When I reject an answer, so I'm very curious about objective functions inside of LLMs at different phases. For instance, what was the objective function when I pre-trained versus fine-tune, now you're saying versus DPO. So when I reject an answer, so some blob of text, what intuition do you have about what's going to happen to the objective function when that sample comes in again? Does that make sense? I'm not structuring that question well.
The objective function in DPO it's about maximizing the difference in terms of probabilities between the tokens in the chosen answer and the rejected answer. So it tries to maximize this difference, meaning that you are going to have a lot more tokens from the chosen answer and a lot less tokens from the rejected answer. I hope I'm right here. I'm not too confused, but so here, what's going to happen is that every time the model sees the rejected answer, it's decreased the probability of outputting these tokens given some context, given the context of your prompt.
So when it's given the context, so that's a condition. So given this particular prompt, does it even go down to the sequence levels? Because it is a sum of probabilities, but are the positions of those tokens taken into account, or just the total sort of cumulative sum of those probabilities? Some math person would get very angry with me.
Yeah, the position definitely matter here.
Okay.
But it's a bit of everything, to be fair. It's really like the hidden representation, the embeddings of the transformers that are used to calculate these probabilities. So it's difficult to really say, oh, it's this one thing. It's more like a combination of everything that is given as input, plus all the pre-trained weights of the models.
And do you see the size of the embedding? So I know we're diving very deep without giving folks a ton of context, but each token inside of an LLM has a corresponding embedding that was learned during training. How have you seen the size of that embedding impact the quality? And is there sort of a cutoff? Is there a minimum? And any insights there?
It's a good question. There's a common recipe to train transformers, to architect transformers, and we now have this kind of scaling laws. Like if my model has this size, then the embedding size should be this or that. The bigger the model, the bigger the embedding layer. But I'm not too sure that this has been properly explored. I would probably assume that yes, some people have written papers about it, but I don't have any reference in mind. So to me, at least it started as a recipe, and maybe now we have a better understanding of the optimal number for the embedding size given the size of the model. But it's basically those two factors, those two parameters are really, really connected, and nobody really deviates from this rule. Now it's set in stone. Everybody follows it.
It's quite costly, right? Because you're basically learning from everybody else's expenses to some degree.
Yeah, with large pre-training rounds, you see that companies tend to be really careful and quite conservative because they don't want to, ruin it. It happened a few times, to be fair.
Yeah, I could imagine what that's like when you're on a high profile team like that and you kick off a training round. Oh, that didn't work, and I spent X number of 100K. What's the first thing that you do? So I don't know how other people feel. I get anxiety multiple times a day when I see 10 new models come out and I'm, compoundingly further behind. What's the first thing you do when a model comes out, if you have the time?
Yeah, it happened a lot actually this past week, I think. So What I do is just like reading like the blog post announcement, of course. Then if the weights are available in the Hugging Face, I will immediately evaluate it because I have my own evaluation framework. And for some reason, these evaluations, these benchmarks, like the name of the benchmarks are quite common maybe, but the parameters vary a lot. You see the same benchmarks used with 0 few shot examples or with 5, and it really changes the results quite a lot. So it's really important to have evaluation that are really standardized so you can compare model with each other and not just rely on the scores provided by the company. Because the scores, yeah, like they a lot of the time they don't even explain how these scores were obtained. So it's really difficult to judge without it. So this is the first thing that I do, and usually this translates into an error telling me that I need to update my transformers library. But when this is done, most of the time, this is good, and it allows you to really compare everything. And oftentimes you realize that, hey, this model hasn't given like any benchmark about code, and it's because it's really bad in code, or no benchmarks about long context capabilities. Well, it's because it's really bad at it, which is fair, but it also gives you a clearer picture, a really good overview of the model, and not just like what's the company wanted you to remember from the announcement.
So you said you can merge models. So can you expand a bit on that? And when you go do model merging, if I know this model sucks at coding and it sucks at math, and I bring in a model that's good at coding and good at math, do you have that level of flexibility to essentially be choosy with parts of models?
Kind of, but I think that your example would be a bit extreme because if you're bad at
Okay.
math and you're bad at code, it means that the pre-trained model is bad, those two tasks. And if that's the case, well, it's a problem because model merging in its current form works by merging the parameters of different versions of fine-tuned models. But what I mean is that they all come from the same base model. You
I see.
cannot merge models across architectures. You could, in theory, merge a model from a base model 1 and another model from a base model 2 if the two base models have the same architecture. But it's really rare to have this scenario in the wild because usually LLM providers only release one base model, so you have to work with only one base model. You could do it if you do continual pre-training, for example, but this is not a super popular technique because it doesn't work that well in practice. So to answer your question, yeah, the idea is really merging the parameters of different fine-tuned models, and indeed you can recover performance. If you have a model that is really good in Japanese, for example, you can add this capability to another model. But what you often see is that if the pre-trained model is really bad at something, for example, code, this is not something that you can really fix through post-training. You will target capabilities that are a bit more superficial. It can be things that are quite important, to be fair, like instruction following, like the IF eval benchmark. It measures like if you add constraints to your prompt, like tell me a joke, but it has to be a poem, for example. Most models are not super good at that, but you can maybe merge a model that is really good at that with another model that is not too good at that, but it has like other nice capabilities. And in this case, you can make a really strong merge model.
When you do merge model, what happens to the total number of parameters? In that case, I haven't done I haven't done any model merging.
So when we talk about model merging, we can talk about just taking every parameter in the model basically and average them together. This is like a good
Okay.
representation of like the naive way of doing a model merging, which is a very strong baseline, by the way. There's more interesting techniques where you're going to extract task vectors. You're going to try to reduce the redundancy in the parameters of different models because we see that, yeah, most of them are kind of quite the same. So does it really make sense to use them? Not necessarily. So you can drop a lot of parameters and focus on the ones that are actually quite different between those models. So this is what I mean by model merging 95% of the time. But there's also techniques that are called Franken merging. And when you do a Franken merge, it can be something like I'm going to repeat some layers in my model. So instead of having a model with like 40 layers, you're going to end up with a model with 50 layers because you repeated some of them. This is something that I've done in the open source. I've created, for example, a Llama 3.1 model with 1 trillion parameters. And to do this 1 trillion parameters, it was actually based on the 405 billion parameters Llama model. I had to replicate a lot of layers. It doesn't make a lot of sense to be honest with you. This was meant more as a joke and as an experiment if someone can actually run this thing. But this can be interesting in some edge cases, but most of the time, Franken merging is funny, but it's not that great. And the traditional model merging is the thing that really, really works well.
Insightful. How do you go about reading papers? And how many papers do you read a day or week? What's the time frame?
Yeah, reading papers is quite difficult because there's so many publications in this area. I think that I'm quite lazy, so I try to read as little as possible, and it's mostly things that I curated through Twitter that I would focus on. So I would just see the same paper once, twice, 3 times. I'm like, okay, probably need to read it at this point. So this would be my strategy. And to force myself to read a bit more and to try to check archive and look for interesting papers. I also try to post about the papers that I read about. So it's something that also helps me to not be passive in my reading, but also read so I can summarize it for someone else.
Do you find that codifies your learning process better than just reading the paper?
Yeah. I think it's really helpful in general. And it's interesting because sometimes I want to post something, so I will read the paper. And this paper can be like a bit further away from my comfort zone. So it's also like kind of allows me to explore a bit more outside of just post training area.
How do you feel? So you have a PhD, right? And you're a quote unquote expert. You've put out a lot of material. How do you feel when you don't know something, but you want to post about it? What's your anxiety level like? And what advice do you have for folks there? Because I think that's what a lot of people feel. They have a concept of how this thing is, but Twitter could be brutal. Folks in the space can be quite brutal if you say something wrong.
Yeah, I post about stuff that I don't know about all the time, to be honest with you. I think this is really how you should write articles in the first place, like blog
Ooh.
posts. It should be something that you're actually learning. There are 2 reasons behind that. The first reason is that, well, at least you don't write for nothing. You write to explain it to yourself. And you know that you have an audience and you know that people can be brutal. So it's always a bit stressful. And that motivates you to do better work and to go deeper in the concept and your understanding of what you're writing about. So I think this is a good point. And the second point is that people who read your articles are exactly in the same position when you started writing about that. So you're actually the best person to explain it to other people. If I have to explain fine tuning to other people, I might actually go straight to like DPO and SFT, and I'm going to miss like a lot of easy stuff that I don't even notice anymore. So I would say that someone who starts is actually very interesting to read, even for myself, because I see what they struggle with, what are the main obstacles, and things that you might have overcome a long time ago because you've worked in this field or in this subfield for a while, but that's not representative of how your readers will feel when they read your articles.
Insightful. That's good to know. So I'm just gonna post. I'm gonna keep posting about stuff I'm not 100% sure, because I don't know, especially as I work at in NVIDIA, you just see amazing people, and you're just, even though you have a PhD, there's levels, and you're humbled quite often. Yeah.
Yeah, I think it's true. And to be fair, like people are not that mean on the internet. I've had like emails, like private emails saying like, oh, I think that there's a mistake in your code, this line. And I'm like, yeah, great, I can fix it. And that's it. So there's a silent majority that is like truly very helpful and very
Yes.
kind. And you're mostly right for these people.
Mm.
If people are angry at you on Reddit or some other website, well, it's too bad. Like maybe they'll like you next time.
Yeah, it's probably some bot at some point.
Yeah,
Anyway.
you can tell that to yourself.
Yeah, you're a bot. So let's talk about the LLM scientist roadmap. And I thought it was a really nice framework that you laid out. So step one of the roadmap is understanding the LLM architecture, which you had 4 parts. And the first part is understanding the GPT decoder style models. So can you explain how this kind of works on a high level?
Yeah, so the distinction here is about the different types of transformer architectures, different flavors. We had like the original transformer architecture is an encoder decoder architecture, meaning that you are going to take some input, for example, a sentence in English, and you want to do translation. So it's going to encode everything in the encoder part of the architecture. At the end of the encoder is going to have like an embedding, so a hidden representation of all the information in your input. And then it's going to use this embedding to decode it and write the sentence in another language if you do translation, for example. So in the decoding part, you're going to extract like all the information from the embedding and be able to this time generate outputs. So encoding is really about learning a representation, and decoding is about generating an output. So the transformer architecture was based on these 2 blocks, and then the BERT model was released, and the BERT model is about just encoding. And by just encoding, what you do is an embedding model. That's how we call them now. And the embedding models are just simple, most of them at least, are just simple encoders. And then a model was released after that, and that was GPT. And GPT is a decoder only model. And I think this is like the most interesting part, at least for this course, because it doesn't try to make you an expert at everything. But if we're talking about modern transformers and large language models, like most of it is this kind of model. It's the decoder only because it's the one that can actually generate tokens that can output text. And yeah, so I think this is important to understand in terms of architecture, the difference between these 3 types. The transformer architecture, so encoder decoder, kind of died with T5. It was a really important model that changed the way that we would now nobody uses it. So everybody has been converted to the decoding architecture. So this is what you should focus on.
Yes. Okay. The second part is tokenization, which takes, in this case, some input text, but tokenization is taking any input data and breaking it up into, I guess, those base embedding vectors that the model was trained on. What insight can you share about building tokenizers for foundational models, if you've worked on stuff like that?
Yeah, tokenizers the worst part in the entire architecture because it's like this ugly patch that we don't want to have. And the reason why I say that is tokenization is the process of converting text into numbers. I have a really good example of that with the cover of the LLM Engineers Handbook. If you look at the cover, I tokenized the title of the book. So instead of reading LLM Engineers Handbook, what the model actually sees is LL, and this is assigned to one token ID. It's 4078 with GPT-4's tokenizer. Then it sees another token, which is just M, then another token is white space engineer, another token is S, etc., etc. So this is why this is annoying, is because the model doesn't learn this tokenization process. The tokenizer is something that you train on a calibration dataset, and you hope that you will not have any issue with that. But sometimes you do, because sometimes this is a known issue with GPT-2's tokenizer. They had a very weird token in the calibration dataset. And if you use this token during inference, well, the model hasn't been trained on it at all, and it would like absolutely destroy the model. You have like a ton of issues with tokenizers, and we try to get rid of it because this is like source of many problems. Every time there's a new release of a model on Hugging Face, what the staff is mostly focused on is not the parameters of the model, it's really the tokenizer and all the configuration files that go with it, because this is mostly where it breaks. When you do fine tuning, this is also your main issue, is with the tokenization process and the fact that you have to make sure that every token in the chat template that you might use has the right token in your tokenizer. Otherwise, like, it might also not break the model, but degrade performance. And it degrades performance a bit, not enough to actually notice it, but it's there. So you have to be extra careful about it. To answer your question about tokenizers, it's really the process of converting chunks of like subwords, so tokens, so they can be fed to the LLM and it could be understood by the LLM, because LLMs do not understand raw strings. It doesn't understand text. It has to be token IDs that then learned. They have embeddings per token, and they combine these embeddings within the architecture to understand the entire sentence.
Do you think they understand our notion of concepts, LLMs?
What do you mean by that?
So we have a concept such as physics, or we have a concept of, I don't know. Well, gravity is an extreme example, but I'm just thinking theoretically, if I have a bunch of these tokens coming in, yes, I go through, we're going to talk about the attention mechanism coming up. Actually, that's a good segue. So the next part of it is the attention mechanism. What intuition you think is learned through that process, given that tokenization is quite tricky?
Yeah, so during the attention mechanism, so you have your tokens have embeddings, and now the goal is to see what's like the relations between the different tokens in your input, and the fact that some of them might be really connected to others. And when that's the case, then it means that the sentence has a different meaning. There's the very traditional example in NLP to say, like, I walked near the bank and I robbed a bank. Well, bank here is the same word, but the context is completely different. And when we speak English, it's very easy to understand that it's not the same bank. But for NLP models, for a very long time, it was a major issue. It was really like a ton of hard-coded rules, or statistics were used to be able to really capture the different meanings of the same word. With LLMs, we don't have this problem because of thanks to the attention mechanism. In part, it has been solved a bit earlier than that, but let's go with that. And if with a transformer, everything is really dynamic. So you see the relation between all the words in the subwords in your sentence. And this is what really matters. And this is why transformers are so powerful, is because they cache all the tokens in every layer of the transformer architecture, and they can compute the relation between all the different tokens to understand what's important. If you have a question, for example, in a RAG application, you want to ask when Napoleon was born, and you have as a context the Wikipedia article about Napoleon, the model will calculate the attention between your question, every token in your question, and all the tokens in the Wikipedia article. And it's going to find the birth date of Napoleon. So it will know that it actually really, really important, and you need to focus on this point. So this is how it works on very high level. I don't want to go super technical, but this is why it's super important. And this is really the powerhouse behind the transformer architecture.
What are the benefits of understanding the attention mechanism for, well, let's say for these two personas, the LLM scientist and the LLM engineer?
Yeah, for the LLM scientist, there's a ton of work related to the attention mechanisms and the way that we can improve it or completely replace it. We improved it with different techniques. The most famous one is called flash attention. And with flash attention, you overcome a main limitation of this attention mechanism, which is, well, as I said earlier, you cache all the tokens in your input, which means you need to store them twice every time to calculate the attention matrix. So it's 2D. It goes really fast, as any software engineer would be able to tell. This is not good in terms of complexity. And flash attention is one of these techniques that actually reduces the complexity in terms of space, in terms of VRAM usage. When you have long context, it's able to be a lot more efficient. So this is really important to know. I think at this point, flash attention is so used everywhere that even LLM engineers have to know a bit about it, because this is something that you will find in every major inference framework. And you also need to know about it when you explore different architectures. For example, you have SSMs, you have Mamba, you have hybrid models. And here the idea is that we can maybe completely replace the transformer architecture or replace it some layers of it. And you have SSM models, for example, that are a really good competitor. And what you do here, instead of caching every input, you have a fixed budget, you have a state, and you will compress your input into this state. So the size is fixed, and the model learns to have a really good compression to be able to answer questions. The issue here is that if you ask a really precise question, you want to quote a part of your input, for example, because the input was compressed, you're not sure that you're going to get the exact answer that you were looking for. So there's a bit of trade-off with every architecture, and understanding how the attention mechanism works also informs you a lot about these different trade-offs.
To some degree, the value of the attention will come, at least from a functioning perspective, will come in the pre-training stage and possibly sort of the inference stage where I maybe, would I train on a different, for instance, if I train on a non-flash attention, can you inference on flash attention? You'll have to inference with the same attention that you did throughout, right?
No, you can actually.
Okay. Interesting.
Yeah, it's quite swappable the way that it's built.
Okay. So that does not necessarily affect your objective function that you learned with initially versus what you maybe infer with. Okay.
No, it's more about like fusing operators at a kernel level and be like closer to hardware to be able to have the right batches and kind of unify operations that were not unified before. So it's really about optimizing your calculations, specific hardware.
Yep. Makes sense. So the fourth part is text decoding. So I have an interesting question when it comes to, so you mentioned that these tokens they're not necessarily human readable words, as you showed on the title of your book. They could come up with weird sub tokens. So when I decode and I see a human readable word, I'm reading a combination of these mishmash of tokens. Is that intuition correct?
Exactly.
So that's almost like a UI kind of thing that any visualizer shows me, right?
Exactly.
Okay. And so the four main techniques, greedy decoding, beam search, top K, top P. How do you anchor that intuition in your mind?
Yeah, so it's important, as you said, to understand that the input of the model is not a string, but it's actually numbers, the token IDs that I mentioned. And the same thing is true with the output. The model does not output text. It outputs a probability distribution. It's not even probability distribution because it's not normalized. So it's more like scores. We call them logits for every token. So for every token, we have one score, then we can normalize it and like get actual probabilities. But this is what it's going to tell you. If we take an example of a sequence, if I write LLM engineers, then I feed that to the model, and the output will be a certain
Oh, that's beautiful.
probability distribution. Thank you. And you will see that, for example, Handbook will maybe have a big score because this is known to be associated with it. At least I hope it's going to be next year with the new models. And this is then, as you mentioned, sampled in a way because, okay, you have a distribution, so I can take the maximum probability in this distribution that is output by my model. This is greedy decoding. You just take the most probable token at every step, and you will create your sequence like this. LLM, what's the most probable token? Engineer, okay, I take this and I continue. This is fine, and this is very intuitive because you're like, okay, like why not? This is what the model is the most confident in, so this must be the right answer. But actually, when you play a bit with these samplers, you realize that okay, it works. But if you try to do something like creative writing, it's going to sound absolutely horrible and very robotic. And this is why you want to add a bit of randomness into this sampling procedure. So we have different ways of adding randomness. You mentioned top K, top P. We have a lot of other techniques to do it. And the idea is always the same. It's about having this distribution probability and what do we do with it. For example, with top P, you're only going to consider the most probable tokens, but with a certain amount of probability, a certain amount of width, I would say, in your probability distribution. And you're going to sample them based on the probability. So if you have a token with 80% and another with 20%, you're still going to sample them with these respective probabilities. Top K, it's about searching with different beams, with different sequences. What's the most likely sequence? Because when you do greedy decoding, every time the token that you select is the most probable one, but you might not obtain the most probable sentence in the end. So you can also try to optimize for the entire sentence. So all these techniques are here to make the models a bit more natural, a bit smarter. And when you compare greedy decoding with some other samplers that are a bit more evolved, you see that humans really prefer the answers from the other samplers.
So when people modify temperatures are a popular parameter with LLMs. What's intuitively happening on the decoding side?
Temperature is going to skew your probability distribution, and it's going to make either the least likely tokens more likely, or the opposite. It can also collapse on like just one super likely token. So it's really interesting to play with, to introduce a bit more randomness, because like an unlikely token becomes more likely, so it's more likely to be picked. And when it's picked, you can write a more interesting sentence.
So temperature, to a degree, I'm very curious about this codification of personality in an LLM. So it sounds like temperature is a major factor in that expressiveness of that personality, yeah?
Yeah, temperature makes the models more unhinged in general. They can start rambling about stuff that is like beyond the question, for example, which is fine when you have a task like creative writing. You want a very high temperature because this is what the model should do. And on the other hand, if you have a task like code or like math, you want something that is a lot more strict. Yeah, so you want to have a lower temperature.
Yep. So moving on to the step 2, which I think is quite important, is the instruction data set. And I don't think many people get to spend time in this phase. What is an instruction data set, and what are some of your best practices for maybe curating one?
Yeah, instruction data sets, they're here for supervised fine tuning. So the step after pre-training. With pre-training, it's quite easy, I would say, because you just have raw text. So this is the only thing that you have. But when you have a base model that was pre-trained on just raw text, what it does is it completes your sequence, it completes your text. So if you ask a question to a base model, most of the time it will ask another question because it's just completing your first question. It's not actually answering it at all. So supervised fine-tuning is here to transform this auto-completion model into a useful assistant that is able to follow instructions and answer questions. So the instruction dataset reflects that because you have two main fields. One is the user prompts, user instruction, and the second one is the expected answer. It's the output that you want the model to give you. So you are going to learn a specific template to tell the model, hey, here's the user instruction, and hey, this is where you should put your answer. So we have a lot of different chat templates, and this is another common issue with fine tuning. A lot of people have problems with that, me included. So with the instruction dataset, what you do is that you only care about instruction and answers, and then the chat template is something that you apply afterwards. But to get the best quality in terms of instruction data, there are three dimensions that you have to take into account. The first one is the accuracy of your data. If you ask a question, is the answer relevant? Does it actually answer the question? Is it the right answer? Most of the time, it's quite easy, but sometimes it can be a bit more involved because, for example, with math, you might need a solver to make sure that the answer is accurate, or with code, you might need unit test to make sure that it can execute the code. Then the second dimension is diversity. With diversity, the idea is that you want to cover a broad range of topics. You want your model to be able to answer pretty much any question that it will encounter in the wild from users. So you really want to maximize the diversity in your data. It also makes the model a lot smarter. So it's really, really important to do. You can control the mixture. You can put more code, less code, math. You can play with different personas. You can do a lot of things here. And finally, there's complexity. And complexity is about really challenging the models to output long answers, to output answers that are very precise. You can do a chain of thought. You can have multiple steps. And by challenging the models to output really complex answers, you also teach it to be smarter and to use this framework like we use in prompt engineering, for example, when we say, let's think step by step. Here, it's directly instilled in the training, and that makes the model better in the end.
Do you add new knowledge to an LLM during instruction tuning, or is it already has this knowledge and you're helping it, even though you can add new knowledge in context? But what's the intuition there?
It's a debate in the community, I would say.
Okay.
I think it depends on your definition of knowledge, because if you have a model that hasn't seen a lot of code during pre-training, you will not be able to really fix it during fine-tuning because it just requires like really a lot to learn code, and you don't have enough tokens to learn that. But if knowledge means, for example, learning that you're a model developed by X company, for example, you want to teach the model that it's been trained by NVIDIA, and you can even insert like facts about NVIDIA. You can talk about things that the model does not necessarily know, maybe because it's too recent. You can talk about like the latest models that NVIDIA released, for example, and that is learnable. That the model can actually add to its knowledge base. And so it's more in terms of scale, I would say. Learning new knowledge is possible, but you have a very small token budget compared to pre-training, so it cannot be super complex task.
I see. So it's really down to the task. So knowledge comes back to this notion of performing a task. Okay.
Yeah, it's a really narrow definition of knowledge, I would say.
Cool. So pre-training was your next thing. Most of us, I don't think we'll ever get to do pre-training. And what are insights that you have on the pre-training side? I think you said certain things about that's the time to learn. So it's almost like your PhD. What intuition you have there?
Yeah, pre-training is quite difficult to learn on your own because it requires like a certain budget. I think it can play with it with small scale models. Now
Okay.
we have really good pre-training data sets like FineWeb and a lot of others that are super high quality. And that's probably the main thing that you want to learn about pre-training. It's about filtering data. It's actually, you have different blocks in pre-training, of course, but I would say that the first one is we have a ton of data on the internet and everywhere. It's actually easy, like we're not running out of tokens. We have a lot of tokens. The issue is how to filter it, how to filter the data to get the pre-training data set that is the most useful, that will give you the best performance. And that is absolutely critical because you can train for 20 trillion tokens and still get worse results than a model trained on 3 trillion tokens. It's just difference of quality. So that would be the first part. And then you have all the stuff related to running clusters, distributed computing, communication between different clusters and nodes, a ton of issues related to hardware, really. This is really nice. You can see a lot of interesting stuff from logs, from research labs, for example. But this is difficult to learn without hands-on experience because here you really need to be the engineer and fix these issues and address them and really be confronted with them to learn it. So this is the part that is quite difficult to learn. But then if we talk about like the algorithms, about the way that we pre-train, like the training algorithm itself, it's actually very easy. It's a lot easier than DPO. It's even easier than fine tuning. It's really about predicting the next token. And there's not a ton of like objective functions here. It's mostly like just this one now. And so then we can talk about optimizers, which is the best optimizer. Should go like scheduler free or not? Because you do very large runs, you probably don't want to mess with that too much, however. So you would go with a kind of safe configuration. And that covers, yeah, like as a high level overview, a lot of what pre-training is. So I would say data is super, super valuable. And for more like hardware related stuff, it's difficult to learn it without hands-on experience.
So steps 5, 6, let me see, 4, 5, and 6. So 4 was supervised fine tuning. So we spent a good amount of time talking about that and we enjoyed that. Step 5 was preference alignment. And then step 6 were evaluations. Any sort of closing thoughts on those three? Because you spit some good game so far on those.
Yeah, those are really the post-training task, and it's a loop really. You create data, you train models, and you evaluate the models that you train, and you use these evaluations as feedback to improve not only the parameters of your training, but most of the time, most importantly, it's about the data itself. So you actually evaluate your data through the model, and the data is what really matters in the end.
Okay.
So yeah, it's iterative cycle. You keep producing better and better models, and this is why evaluations are so important. It's because if you optimize your entire training stack to produce some results, you're going to make sure that the results are actually what you care about and you're not just hacking something, because in this case, you might just work a lot for nothing.
Wow. Yeah, it's a good amount of compute that you could waste as well if you're not.
Exactly.
Yeah. Okay. Is that quite stressful to to work in like that, and you have an idea but you don't know, you have a certain amount of tries on an idea?
I think it's okay. It can be mitigated when you have a lot of different benchmarks. You get a ton of signals, and then you also learn that some benchmarks are more reliable than others, and you keep adding more benchmarks. So it's okay in the end, like as long as you have a comprehensive evaluation framework, I think it's fine. But if you work with just like full benchmarks, like for sure you are going to optimize those four and probably degrade performance on pretty much all the other ones.
Yeah, very good insight. So quantization, that's where everyone tries to save money. We try to reduce the precision or the size of the floating point numbers that we do math with, or integers. Tons of interesting things about in there. So I wanted to get your feedback on this. Just kind of hit me. So in an LLM, we have weights. So I can think of those as the brains of the model. Then we have activations. I think of those as the thoughts of the model. And then the KV cache, which is just essentially the spoken words of the model. What's your, did I hit it in intuition? Or would you add or subtract from that?
No, I think it's correct. Yeah. And yeah, when we talk about quantization, actually, it's mostly the parameters and not the activation so much, for example.
Okay, that's good insight. So a lot of time, so if people are focusing on quantization, they should just focus on weight quantization for the most part.
Different techniques to do it, and we see more and more like activation aware quantization or quantization applied to both weights and activation. But yeah, it's mostly successful with weights. Activations are a lot harder to deal with. But there's a lot of research in this area, so we might have something a lot more
Some new things
comprehensive.
coming out.
Yeah.
And quantization, just for those listening, that we're just doing range compression, right? To speed up math, essentially. Okay, so this was fantastic overview of the LLM scientist roadmap. My last question on that piece is, what do you think the roadmap is for the multimodal scientist? What's your intuition there of what they may need to delta?
Yeah, multimodal models are really based on the same ideas. So I think you can just add extra chapters
Okay.
dedicated to some modalities, but the bulk of it is pretty much the same. Like you also do tokenization, you also use decoder only or encoder decoder architectures. So yeah, this is pretty much the same. I would add maybe one chapter for image. And by image here, I mean mostly vision language models. So text plus image to text. Could also do text to image, for example, but that is a bit different. So I would not really explore it here. Another chapter would be about audio, because audio also is also very interesting. Like people want to just talk to the model and get some output, for example. That creates a lot of interesting use cases. And audio is quite peculiar too. You have a lot of subtleties to understand well, and there's a lot of different implementations of it. So yeah, this would be my main thoughts.
You might get hustled into doing a new book.
No, not again.
Oh, cool. So rounding out, well, I have a couple more questions, but what's your career optimization function? Is it wealth? Is it interesting work, knowledge, enjoyment? How have you architected your career so far?
It's a good question. I think it's a bit of everything, of course, but I feel like I've always been directed. I always try to work on the topics that interest me the most. It started with AI. Like I have a cybersecurity background, so I really started playing with AI and implementing neural networks at the beginning of my PhD. And I realized that I liked AI a lot more than cybersecurity. So I really just kept working in AI instead. And then there was some architectures I was really fan of, and that also guided me to work for JP Morgan, which was interested in this. And now at Liquid, I realized that what I really enjoy doing in the LLM sphere is the post-training work. It's really about everything that I mentioned previously, like the problem with the evals. I really love that. Creating instruction data that is super high quality according to the 3 dimension. This is what I like. And no, in general, it's about being very crafty. It's about finding hacks, finding new ideas, and you don't need to be Google to find these ideas. Actually, a lot of the time, like the open source community is super creative, and like a bunch of monkeys, they manage to create some stuff that is then reused by all the major labs. And this is quite crazy. When you look at model merging, for example, This is something that I found like completely stupid. But at some point I had to try it, and I tried. And at the beginning I was like, no, this doesn't work. And then I saw the result and was like, maybe it works actually. It works. And now everybody uses model merging. Everybody, like all the major labs use model merging. They would say that there's been like also academic work on that side for a while. But I think that the way that the open source community also use model merging with tools like MergeKit is something that was very important for the widespread adoption of it. So this is really my kick in this field. It's about like these stupid ideas that turn out to be really, really great and really fundamental in the way that we train these models now.
That's pretty cool. So the landscape of jobs and careers, I think, is going to change to some degree, especially as data scientists. How would you approach the market as an early career professional, especially in the US, in addition, also in a small region? So I come from a small country in Trinidad, very different kind of vibe. Opportunities are not there. So I think your contributions in open source, really open doors for folks who don't have access. But what's your thought there?
No, it's a very good point. I think that the open source contributions that you make are really, really important to leverage good position early in your career. You can do it like pretty early. It probably works better if you have like a few years of experience already, because you're basically safer for employers. But even like early in your career, if you're passionate about it, it's a good idea to just go to Hugging Face, try some stuff, learn about it, find the paints. For example, I mentioned the fact that there's no high quality preference data sets online. There's some, but not that many compared to instruction data sets, for example. So this would be a great way to make a super useful contributions. And by doing that, you're going to meet a lot of people, and with these people, you're going to have other opportunities, and this is how it grows really. So I would really recommend doing open source work if you're interested. And if you're not, I think that you can definitely just find a good position, and from that work to get into the stuff that interests you more and keep climbing the ladder that way. But for sure, showing your work in general is something that really works. And even if you do not want to do open source contributions, I think that joining a company that allows you to show your work openly, publicly, is something that is very valuable in the long term for you.
Yes, absolutely. So hopefully you have about 2 or 3 minutes. What 3 books do you recommend people read besides the LLM Engineers Handbook?
Oh, I don't remember the names.
Okay. No. Are you a big reader in general?
I don't read that many books, to be fair, but I have one that was sent by a friend, and it's the LLMs for building LLMs for production book, and that's
I saw that one as a recommendation. Okay, cool.
It's also a good one, and there's the one made by Chip Yuan, and I don't remember.
That just came out. Sebastian's book was good as well.
I would also recommend Sebastian's book. I only checked the repo, the GitHub repo, to be honest, but it was really high quality. So this is definitely a good idea to do.
Yeah, between the 4 of you are doing amazing work. What's one piece of advice that you have for a high schooler, a college student, and a professional? It could be the same or it could be different.
I think that you can do work that you don't like but pays well, but in the end it's better to do work that you enjoy, because you will outperform all the other people that do it for the money. And as an advice, as a career advice, I think it's really good for you to be in a position where you can choose to do something that you enjoy. It doesn't have to be like the biggest passion of your life, of course. It doesn't have to be like your hobby and your work, but if you really take pleasure in it, I think this is really stupid career hack, because you work more without feeling that you work more, and this allows you to be a lot more proficient too, compared to a career that you only do for the money. This is my view on it, and this is also why I try to target positions and roles that interest me, because I know that it makes everything a lot easier, to be honest. So this is a good like greedy strategy to me.
I like that. And I could see, like, I feel that in this interview, Do you enjoy explaining all these things? I could see your face light up. So it's cool that you found something good, although I imagine it's quite painful.
I have other hobbies, I promise. It's not just frustrating LLMs.
Cool. So my rapid round of 3 questions. What's one thing that brings you joy outside of LLMs or post-training?
That brings me joy. Well, I think it would be something like a family, like my partner, things that are really a lot more social than it. And if it's more an intellectual topic, I'm really into history, for example, and I think it's
Okay.
really fascinating. Yeah, this is something that I read about like every day, and like as an intellectual curiosity, it's something
Yes.
that is completely related with my work that I really enjoy.
Fascinating. So you're stuck on an island. You have a specialized chef that can cook anything. They could fly in any ingredients. There's no constraints. You're going to be stuck on this island doing post training for the next 10 years. And you only get 2 meals. What 2 meals would you have that chef make?
Oh, it's 2 meals. It's a very difficult question.
Yes.
It's a good idea. So I think I would take like one dessert, and one main meal. I would order a raclette, which is like this Swiss/French dish with roasted potatoes, a lot of cheese, and some salami, some kind of ham. It's really hearty, and I think that I can live on it for 2 years or for 10 years quite easily. And yeah,
What's your dessert?
as a dessert. Uh, Maybe just ice cream, honestly.
Ice cream. Okay. I haven't heard much people call out dessert on this question. So it's interesting. Most people just focus on the food. But I'm with you on the dessert camp. It's important.
Because after the raclette, actually, I think I'm going to be very full, so I need something a bit lighter to finish the meal.
Makes sense. And last one, what would you do if I gave you $1 billion? Or what would you do with it?
Yeah, I would try to get rid of it, probably, because I think it will create a lot more problems than it will solve for me. So yeah, I think I would try to give away a lot of it to charity and do my own stuff with the bit of the money. I think I'm really happy where I am right now, so I'm not sure I would just like quit my job or anything, but it's good for future me when I'm tired of post-training. I think I will enjoy it. I can create video games and not worry about the money.
Nice. Maxime, I want to say I've enjoyed the interview, and I thanks for sharing your intuition and post-training me in this episode for the most part. And for those listening, definitely grab the LLM Engineers Handbook. I will be grabbing my copy soon.
Thank you very much, Mark. Thanks for the invite.